with that, I'm off to start. Welcome everybody. Thank you for joining me. Whoever is in Zoom, thank you. I would like to express my gratitude, Dr. Vito, chair, the rest of my committee. It's a large committee, but thank you. I'll be defending what I call the evaluation of machine learning algorithms in accuracy and in energy exploration using physics-derived synthetic models. That's the overarching question. So with that, of course, yeah. So I know it works perfect. So my overarching motivation is the application and evaluation of machine learning techniques for subsurface, right? That's what most of we do here, at least with Dr. Vito. And then I'm adding a little bit of characterization, risk assessment, and uncertainty quantification in energy exploration. My main input is seismic data, so we're talking about seismic data a lot, but I will also include some borehole data. So these are my three overarching research questions on how different machine learning algorithms, such as generative adversarial networks, henceforth GANs, self-organizing maps, hierarchical clustering, can help us in harnessing the speed of machine learning. So what are the advantages and limitations using physics-derived synthetic models? Since we can generate a synthetic model based on whatever, but I'm trying to keep it a physics constraint. So that will be one of the strong points of this talk. And what are the advantages and limitations of using different kinds of seismic inversions? My second overarching question and motivation is enhancing decision making, since now we have a truth model that we can always go back to and evaluate how our models are being processed. That's a good way to understand the uncertainty. So I will be talking about just one chapter, as Dr. Riddle said, but let me introduce a brief dissertation structure. So chapter 2 talks about GANs and how it's creating reservoir models from rock physics informed training. And then chapter 4, it's using hierarchical clustering, which is a more simple machine learning algorithm in the prediction of fault and the prediction of seal risk and fault juxtaposition. And then I will be contrasting random forests and recurrent neural networks, RNN, for us friends, and in the in-situ water saturation. So let me make a quick tour to generative adversarial networks. So in this chapter, it was my first chapter ever written 3 years ago, and I struggle a lot. I just picked it up maybe 6 months ago, and my main motivation was GANs. It's an algorithm to networks that are generating fake data, but how can I provide like truthful and well-established training data? And that's why I included the rock physics modeling and the geostatistical inversion. So the geostatistical inversion and the reservoir water saturation provides good images of the reservoir, and then I use GANs, or I feed it into GANs to only make these models. So of course we can use seismic attributes, but seismic attributes is not something that we can measure on the lab. So that's why I think this is the first rock physics model that is worth mentioning. So this is a result of stacking all the GANs models, just vertically stack them. So it's providing good discrimination of what are the base phases, and the limits of the reservoir, right? So that's the general conclusion. Now for hierarchical clustering, so Pierre Cram, 2021, 2022, he did a fault juxtaposition analysis using conventional methods where he calculated the sandstone, the clay distribution on a seismic data set, and then use a fault juxtaposition analysis. However, I'm skipping that process of geostatistical phase simulation, and I'm using hierarchical clustering with a subject matter expert on determining how many phases are correct. And then this is the borehole, one of the boreholes. This is the lithological evaluation, the lithotypes, and then this is the clustering. So it's matching well the gray with the shells, and then I'm just stacking laterally the fault probability. And then my last chapter, recently accepted, with revisions, where I compare different kinds of inputs on the current neural networks and forest random forest simulation in water saturation prediction, and then I just do a special correlation to show where there are more and where is random forest predicting less. So that's for hopefully for publishing next June. So now other peripheral projects that Dr. Bill was talking, conference, just to mention a few, the carbon capture and use 2023 joint impedance inversion, image 21, my first conference, improving deep learning fault prediction using augmented training data. Then co-authors rock physics modeling, I enjoy doing a lot this one in the Brazilian Equatorial margin channels. And then last year with Dr. Chopra, Dr. Murphy, Dr. Vito, the impact of the spectral balance using seismic data in unsupervised classification, where we use GTM and SOMS, with I will be discussing in more details. And then as a first author, interpretation to last year, using seismic to characterize Levi splice in submarine channels, and using unsupervised learning to contrast different fault styles from volcanic inclusions and salt domes, and using remote sensing data attributes such as hill shade and deep azimuth to contrast it with seismic. So the seismic experiment, I don't want to assume everybody is an expert. So we have a source, an energy source that gets into the subsurface, and then it gets recorded back with the reflections. These reflections are carrying the properties of the Earth, and then this mainly will have to do with velocity and density, which is the impedance. Then the wavelet that is the source is convolved, and we generate a zero offset trace. And of course, if we have multiple traces and multiple geophones, we'll have a seismic section. And the attributes that we're recording are geometry, plus amplitude, negative amplitude, and zero amplitude. And then we can extract some frequency and other properties, right? So, and then these other properties, of course, we all know it's a function of a scale, right? So for example, a sandstone that it's a sedimentary rock composed with different minerals will have different sortings, different components, and then it will have different porosities, which we're interested in any case. Either we are injecting fluids for geothermal or extracting gas and all. So that will be high and low porosity, which in high porosity we see more blank space. In low porosity we'll have lower or small blank space. But this sandstone can also be seen from the space, right? From satellite images, we see a couple of radio channels, most likely with some sandstone in it, and from this channel we cannot infer any property, right? Just the shape and the geometry. But for years of application, now we can say, oh, probably there's some sandstone, there are some boulders, maybe some clays over here. So this segues to how we are recording the subsurface, right? So this is Navajo sandstones on a field trip with Margaret Chen from the University of Utah. So I overlay what I would say is an amplitude section, and we only are recording, again, positives, negatives, and to any interface that we can associate. And of course, this is going to give us a different level of different deep of understanding on the properties of this sandstone, which summarizes from a rock. We can zoom in, and then if we record this point, we'll have a very high porosity. If we record this point, maybe lower, and then it will change, and then it will stabilize in an harmonic succession to get the representative porosity of this rock, right? This is a thin section with different mineral components. So how do we tie that to the amplitudes of positives and negatives, right, that I was just telling you? And these amplitudes and positives can be on the order of 50 to 10 meters. So that's about the Sarkis building, maybe, or a couple of storehouses. And that we could correlate using rock physics to the rock properties on the water, right? So In a nutshell, this rock physics and this informed training can help us to model the properties that are soundly established with theory, right? So there are different ways to do synthetic modeling. I'm presenting three, and I will be covering in detail this one and a little bit of this one. And so we have a convolutional model. So from a geological base, we can have any geometry that we want, and then we convolve that. However, that convolution does not carry any amplitude information because it's just one big convolution. So that's one way. So the forward modeling will be to do the full wave experiment, and then the amplitude will change with as a function of offset or an angle, and as a function of the properties that we are modeling. This is density, for example. And then we will record the shot gathers, and then we can do the model forward. Or we can do a full wave equation, and then with properties and geometries that we define, we can include how the amplitude changes. So as a summary of the workflow, we have to define the geometry needed. So please don't use a geophysicist to define this. This has to be a geology expertise with a clear construction of how the faults are correlated, how a dome is formed, and how an anticline is formed, right? Then make a mesh and velocity model with geological layers that where the geophysicists might get its hands on. But this is ideally with the borehole data or mineral data to inform this decision. Then select the model generation that I was mentioning earlier, either convolutional, forward modeling, or generative adversarial networks. Add the desired noise to adjust the parameterization, so which kind of noise we want to add to include either random, spectral balance, or just coherent noise with an impossible situation. So for example, this is noise-free, 1D convolutional layer that I did to train a fault model. So we can see the listic faulting nicely, then some faults to complicate the model a little bit. But then I started to get creative. So I put a wave propagating in the horizontal direction and making this coherent noise. So, and random noise added. So this is where the deep learning algorithm completely collapses. So let me focus on this one. Yesterday it got accepted with revisions, which I think is very positive. And I'm going to talk in detail on the analysis of unsupervised accuracy in detecting changes in reservoir fluids. So the general takeaway point is that GTM, which stands for Generative Topographic Map and SUM, which stands for Self-Organizing Map, they can very well detect the shape on the container, but it struggles with detecting the subtle effect of gas, oil in the amplitudes. To evaluate this, and my motivation, sorry, as I mentioned, evaluate the efficiency of these two methods and attributes to create a classification of the fluid response. So what is the detection limit on seismic amplitudes related to amplitude versus offset or amplitude versus angle effect? How accurately can self-organizing map detect these changes with using seismic attributes? That is a common methodology in the literature review. And thus SOM using seismic attributes can delineate the hydrocarbon types without considering the lithological effects. So this is, for example, a pre-velocity model that I make with a wedge model. And here we can observe a gradient that I include to simulate a high porosity, right? Please close to us, to you. And then as we move deeper, it will have lower gas saturation, lower hydrocarbon saturation, and then, of course, higher brine saturation. And at the end of the model, it's 100% brine. So why a wedge model? This is a very good question. Multiple models in the literature review are providing this kind of models, but they have a deep lithological effect related to the shape. And of course, I'm not a geologist. I could say that there are some channels that are mixing together, and they are stacked channels. And this is a very nice model from the Stanford characterization project from Castro et al. And then in 2015-13, they modified to include the production effect. but it was always getting in the middle. Like I cannot say 100% that I was detecting the fluid effect. It was always detecting the electrological changes. So a wedge model is typically used in seismic evaluation and attribute selection to evaluate the tuning thickness effect. Because naturally, as we go closer and the frequency changes, we will have a harder time in discerning the limits of this wedge, right? And while a simple reflector it will not change its response, as we go closer to the edge of to the limit of the wedge, the amplitude will change. So that's why I summarize it with a double wedge effect, which will have two wedge effects, right? And then I will put three different reservoirs, honoring the physics of buoyancy. So gas will be on top, since it's not as dense as oil. Oil will be in the middle, and water or brine will be on the bottom edge. So some attributes that I will be dealing: amplitude, volume technique, and you can see its effect on the wedge models or coherent energy. And as you can start guessing, there are different ways of attributes to display these wedge models. So the first thing that I did is take an average sandstone, have the mineral composition from quartz, clay, feldspar, calcite, cement. This adds to 100, I hope. And then the shear modulus of each one of these parts, of each one of these minerals. And of course, there could be different ways to mixing. I'm not going to go into details. Hopefully, it's in the thesis. And then this mineral composition can come from a ternary plot, from a core data analysis, or it can come from a compositional mineralogy analysis. And each one of these minerals will have a shear modulus, a bulk modulus, and the density. Those are elastic properties of the material, which we can measure. So a simplified methodology from minerals to seismic. So they simulate the lithologies and mineral composition we want, then run the rock physics model to define which porosity and water saturation we want, delineate the shape of the reservoir, and run the synthetic modeling. At the end, estimate the seismic attributes and the machine learning algorithms that we want to test. And of course, this is a test on unsupervised classification, but this can be extended to supervised classification. So these are the rock physics templates for porosity, the constant cement model. We have the bulk models for different porosities, which are exhibited here. The highest porosity honors MAFCO critical porosity model, as I'm setting a limit of 38%. And then as I decrease as I decrease the porosity, the mole modulus is affected and shear modulus is affected. So once these models are generated, we have a acoustic impedance model, one trace, a BPDS ratio, density, the fluid rock types, as I was mentioning, gas, oil, water, and there's always a mix of them, since we don't have anywhere 100% gas saturation. I will have a ratio of 20%, 30%, and then I will have a residual gas of 10% on the blind layer. So these are the models for the three different reservoirs that I will be calling reservoir 1, reservoir 2, and reservoir 3. And these are based on the range of porosities that I'm giving. Reservoir number 1 being the shallowest, has the highest porosity. Reservoir number 2, the intermediate, it will have the intermediate values of porosity. And reservoir number 3 is the deepest one, that will have the lowest values of porosity. And this model is also including pressure and temperature. So just to have a quick map on our minds of how these three reservoir models are built. So on the grids, on the mesh size, so we have 80% of fluid saturation or of hydrocarbon saturation here, and gas, oil, brine, and then this will be the good reservoir, or the high porosity reservoir. Intermediate porosity 25 to 15, and then the same gain. High saturation, high saturation, high saturation, and it has a gradient to lower saturation towards furthest from you. And then same gain, low reservoir number 3, low porosity, high saturation of gas, high saturation of oil, and high water saturation. And these will form the oil-water contact, the gas-oil contact in all three reservoirs. So we'll have three flat spots. So in 2D, this is how it looks like the impedance models. So we have our background that I named shale with shale values. We'll have reservoir number one, the three flat spot or the three fluid contacts, and then reservoir number two is impedance, reservoir number three on liquid ratio, and density on well, to show three of them. It is important to mention that as we go deeper, the fluid effect is well defined in the density, for example, in BPA's ratio and density, right? But for the last reservoir, since density, the porous space is so small that it's easily blending with the background, right? And even having a slightly higher density. And the same here happens with impedance reservoir number two, the first gas contact. It will have a very similar impedance value, and of course it will have a different BPS ratio. So these values are the ones that will be controlling the ADO and ADA effect, and that's the ones that we are looking for. This is how it looks in 3D. So we have a wedge model with the three different reservoirs, and then if I add some opacity, and hopefully this animation goes well, then I can isolate the reservoirs, right? This is how it looks in seismic impedance, seismic section, full stack, near stack, mid stack, and far stack. These are varying with angle. And I added some spectrally balanced noise to make things a little bit more realistic. Also, I tried these methods with a real observed data set. So let's say that someone gives me money to drill here. I drill Sonor's number one borehole. So I will find a good reservoir, and then I will have gas, oil, water contact, right? And I will get these logs from this borehole, and I will be using that later on for seismic inversion. Before jumping into seismic inversion and machine learning, seismic attributes that have been around for 40 plus years. For example, they are useful to characterize and find other properties of the data, geometries, amplitude, phase. And for example, I'm here overlapping multispectral coherence with the amplitude data, and I'm highlighting how this canyon system has a channel display here, breaking what I call breaking the levee here, right? And this is not common since it's on a high slip. So as today we have hundreds of attributes, right? We have more than we can count, and part of our job is to define which ones are meaningful to us. We have ways to do that. Principal component analysis will be one way to identify the eigenvectors of the matrix. So we have one way to do it. That's the histograms, and we are defining which attributes have the highest contribution to the principal component states. However, I'm a little bit more visual. I like to see shapes, colors, and direction. So, for example, with this vector plot, I can analyze the direction of each one of the attributes and its contribution as a color font. So we can see that these attributes with higher or larger vectors, they have larger contribution than these other attributes. So from this extensive list of seismic attributes, I will select just the most important ones, the first 6. And before jumping into machine learning, while doing the PCA, I started to do some classification, some clustering, and as I was plotting the clusters, I started to realize that the more number of clusters I demand from the data space, there was more overlap between the reservoirs. So which is not ideal, right? Because we want to identify the gas contact from the oil contact in all 3 reservoirs. So in theory, this seismic data set will have 9 different phases or 9 different clusters. So that's 3 gases, right? 3 oils, 3 waters, on the background, right? So here I am plotting as a function of its importance for each one of these clusters, which attributes are more important. So that's an indication. That's a first indication how the unsupervised machine learnings are going to be, and that portion of the data serves as an exploratory data analysis. So I don't want to assume you know SOM, but everyone that we have been relating from here have used some sort of unsupervised classification. So self-organizing maps, we have a grid of points from our collected data that will be the latent space projected in 2D. And then we are modifying the mesh so it can adjust or fit into the most representative or repeated clusters, right? This is from a formation on North Sea that I work with Dr. Chopra and Patel. So we are starting to compare self-organizing maps. So we are starting to see some facial definition based on self-organizing maps. Now, for the same formation using GTM, we have way more definition. Since GTM it's more convenient for highly nonlinear data, which is something that we typically have in seismic exploration. So generative topographic map from the same grid, we're assigning initial probabilities that are fit into a probability plane, and from that we are starting to cluster using reducing these sizes. So all these attributes get mixed into SOM and GTM in my analysis. So here's the first result. And again, this is the view of the wedge model closer to you, where there is higher saturation for all the three reservoirs. We have the outputs of SOM and GTM are two projection axes because it's a map. So the first thing that we're starting to see is that GTM does a very good job for reservoir number one, the gas lake, but then it starts to fade away its accuracy in detection, or we cannot easily detect the shape of reservoir number two and reservoir number three. The gas cap on the reservoir number two, it's completely unclassified or misclassified, since it has a smaller amplitude and impedance effect or contrast with the background, and then it does a very good job in classifying the oil cap and the brine cap. So, and then for the third reservoir, it does a fairly good job in classifying this, right? So in general, GTM is detecting the shapes of the reservoir, but not the minutia on where the fluid contacts are. So these are the labels that we have available to say this is the gas, oil, brine, this is gas, oil, brine, and this is gas, oil, brine. And again, we can see that the first reservoir for gas is completely overlooked. And this will be a happy accident if we drill it, finding the gas cap on top of that or more hydrocarbons, but that's up to the petroleum engineers to define. Then again, let me use my notebook. We are no longer in this plane. We are in the middle of the plane, right? Where we have a gradient of the saturation. Okay. This is more illustrative. So we are in the middle of the model where we have lower saturations. And then it does a very good job again for detecting the gas cap for the first reservoir, nothing for the first gas reservoir number three. And for reservoir number three, it's doing a good job in detecting the general form, but not in detail the fluid models. We have the gas, the body shapes available at this portion, so we can plot our findings. Now let's go for S1. One thing that first needs to come into your mind, and this will be the first takeaway point, is that SOM, it's more stable, looks cleaner. So this is at the reservoir model, at the gas cap. It has less noise around it, right? Which is good, but at the same time, it loses detectability. For example, this is reservoir number one, reservoir number one, and reservoir number two for the gas cap. It's a slightly defined, and here it's a slightly defined as well. But when we go deeper into the model, we are starting to see that the detection of the gradient, of the fluid gradient overimposed with the elastic properties, it's faded away. So at the same time, it's less noisy, but is less sensitive, which means it has less detectability, right? That's one strength and one weakness from SOM. So we have the models to treat or labels to treat our classification. So let's compare these two. GTM on the first reservoir at the gas level, it has a very good extension of the model. This is this limit is defining the 20% gas saturation limit. And even though it's not complete, it's better than the self-organizing maps. So if we remember, and I want you to keep that in mind. So first we have a wedge effect, which is making amplitudes on the seismic section higher with any physical reason, but rather just a mathematical effect. And then for the reservoir number 2, which the elastic properties are very close to the background, it's completely undetected. Even though there's some reflectivity, the contrast is so small that it's not detected. So for GTM to find this limit with a 20% gas saturation, it's very good. It's a good accomplishment. For SOM, even though it's easier to define limits of the reservoir, it is not that good. That it's so far away from 20% gas saturation limit, right? So remember the tuning effect. Here we have it. Here we have it exaggerated on the GTM, and then reduce it on this SOM. Could these two be complemented to find the real limits of the tuning effect? That would be a good question for later. Of course, I run it on a real data, the real data or observed data. It had boreholes, it had partial angle stacks, similar to what I did. I conditioned the partial angle stacks, and I did a simultaneous seismic conversion on that, and also I run the same seismic attributes that were the lessons learned from my synthetic to evaluate this amplitude-dependent prospect. So, as you can see, there is a lot of variability. Even though it's an area with a rapid progression of sandstone and shells, but when I'm detecting or trying to detect the reservoir model, SOM does a very good job in detecting the main reservoir. This is the Steve Barrow reservoir, but it's detecting everywhere else. So not everywhere, but outside. And these are probably the continuation of the fascia, since this is a shoreline reservoir, right? So just to start introducing seismic inversion, remember that we have from a reflectivity model, we have a seismic section, then seismic inversion in a very simplistic way. If we are convolving or multiplying the wavelet with the reflectivity trace and to get the amplitude changes, now I'm divided. And this division, of course, has more to do with forward modeling and inverse theory. But for now, I hope it does the job. And from the reflectivity series and the amplitude, now I'm recovering there. So this will be one of the strongest point of seismic conversion, which does not have the tuning effect, because it's removing the wavelet. So the two flavors I contrast: deterministic seismic inversion. This is simultaneous seismic inversion. Simultaneous seismic inversion workflow. We have our boreholes, we have our seismic stats, we have our interpretation. We extract the wavelet at each borehole, and then the output of this is three outputs: P impedance, S impedance, and density. Or if you want to parameterize differently, it will yield a BPDH ratio. I refuse to use lambda rho at this point because it's just the square root of an accumulation of these two, which exaggerates interpretation effects, but also exaggerates errors. From the geostatistical seismic inversion, we have a variation inversion from a diagram of the elastic properties. We generate multiple seismic such seismic volumes that we fit to the observed data. And with that, it outputs three, and commonly only three impedance models, which is the P10, mean, and P90. However, this is not a reservoir model. This is just an extraction of impedance. And then we can use some reservoir engines from inversion. For example, the fluid and phase probability, the petroelastic seismic inversion, or rock physics plots from Asvet et al. And the same thing with this, right? We can use the three impedance, the three SS impedance, and the three densities for doing one model for all of these. So one ring to unite them all. So the seismic inversion of the wedge models, you can see that there is a wedge effect. That's already a start. And again, this is from our Sooner 1 borehole, pseudo borehole. The recorded information, of course, the well type, it's easy peasy. There's not a lot of stratigraphy to worry about. And then the correlation, of course, is the correlation between the observed seismic and the synthetic seismic from the borehole. So the inversion results are impedance, S impedance, BPDS ratio, and density. So impedance was a problematic one because the reflectivity was close to it. However, the S impedance is here to help us, which is detecting very well the limits. And BPDS ratio, it's also doing a very good job with it. The density, it's always unstable, but it's still giving three different reservoirs, three different models clearly, and a combination of these models allows for a deeper investigation. So at this, with this, I'm summarizing my chapter 3. So model building synthetics should be constrained by rock physics models to have meaningful amplitudes based on rock physics theory, AVO, and AVI effects. Then convolutional models, 1D of a velocity model with whatever geometry we want to impose, does not have the amplitude effects. And then synthetic algorithms improve the decision-making process by understanding the strengths and weaknesses of machine learning algorithms. And sorry, you will have to see this. This is a sweep from the bottom of the reservoir of the model from GTM to the top. And as you can see, here we see the second reservoir coming, and then we will see the first reservoir coming and its variability, right? We can agree that that there is some good effects on that. That the GTM it's finding the overall limits, but with a lot of gaps and not finding the true limits of what we could establish. And perhaps this could be a problem of economics. That 20% gas saturation could be economic. So in conclusion, comparing axis 1 for reservoir number 3 and reservoir number 3 on SOM, we will see that SOM for reservoir number 3 it's almost completely blank, except for a slight indication of the limits, and GTM requires a lot of interpretation to make sense of what the values are making. So what would be this? The limit of the reservoir. This would be the highest portion of the reservoir or the extension. If I were to put a delimitation, well, where would I put it, right? Should I put it here? Should I put it here? That's an added uncertainty that of course we can prove with a synthetic model since we have the labels for this. Yeah. So the dissertation conclusion is that the mechanism, the noise selection, and the property values we input for the synthetic model, it matters a lot. The machine learning clustering effects are useful to detect seismic phase changes in general, but not to detect the fluid effect. And this is a conclusion from what I just showed you in the chapter number 3, and also in the chapter number 4 on the CO risk analysis. Generative adversarial networks is a pixel-to-pixel model generator that it's easily transferable to other projects, although it is making fake data and other attributes, another well-established engines can do that. This is done at a fraction of the time. Then subject matter expert in training improves the classification and regression tasks in machine learning models. Use it in geoscience. This is a conclusion of chapter 2 when I'm doing the generative adversarial network. but also in chapter 5 when I'm using workflow data to predict water saturation using random forest or seismic two attributes are image quality dependent and seismic inversion is quantity data dependent. So there's always a threshold, the trades and whatnot. But we always would like to include or integrate a balance between quantity and quality, right? And even I like random forest. It's a very good algorithm. The strong suit is that it's not easily overfitted or even probably not overfit at all. But it does not reach the accuracy that the current network was reaching. And perhaps that's because it's overfitting the model. And this is one of the conclusions of chapter number 5. Selected reference as a standard protocol. And then, of course, my acknowledgements to all ASPE and Geoscience sponsors. I use the Vito for modeling, SEG, APG for the scholarship and whatnot, Jason, CGG for Hampson Russell, SLV for Petrel, TechLog licenses. And yeah, that's the whole journey. Thank you, Dr. Vito, for rescuing me from Pemex. It was such an honor being here with you. I had a lot of fun with everyone. I'm thankful for all the meals we have shared, drinks we have shared. One of the best experiences was the Toronto field trip. It was very nice. Sadly, my wife could not be here, but I'm sure she's happy. And some friends are here. Some friends are here. My brother is here. My dog is at my home, hopefully relaxing. And some friends that are not here already, but I really miss them. And this is a quote or a paraphrase from one of my favorite artists. And I would like to say total thanks with that. Thank you very much.